Hi again, Corey Adams, once again. I'm up here to talk to you about the deep learning frameworks on mostly Polaris. Things that I say about Polaris will also apply to Theta GPU. I'm going to focus on just some of the basics and single device techniques, and Huiho will follow after me and talk about how do you run these deep learning frameworks at scale. So the three big deep learning frameworks at the moment are Tensorflow, Pytorch, and JAX. We support all of these on our production systems. They all have mostly the same core elements and different strengths and weaknesses. So some of the things you get with these deep learning frameworks are automatic differentiation, GPU offloading, and acceleration without leaving Python. Building blocks for machine learning models. There's usually an ecosystem of extensions. They're all open source. You can typically export a trained model to some other framework, format, whatever, and run it from C++, for example. Pick the one that makes sense for your problem. The oldest framework that we support is probably TensorFlow. It was developed by Google, excellent performance on both CPU and GPU. And of course, if you look at Polaris and Aurora, you might ask, why care about CPU? Some people take a model that trains at scale on, say, a big GPU cluster and need to run CPU-only inference. So if you need to do CPU inference, TensorFlow is typically one of the best choices. Is the mic still on? Can you hear me? Okay, you can hear me. Only TensorFlow 2 anything is officially supported on the ALCF systems. If you need something from 1.x, whatever x is, and you're having trouble installing it, feel free to ask us. And I put a bunch of links here on the TensorFlow basics. Keras, that's their high-level API, mixed precision, XLA. Feel free to get the slides and click the links if you need to deep dive into any of these, or ask us during the workshop. There's not examples that I can come up here and show you that are better than what TensorFlow has themselves. So if you need to go learn TensorFlow, you should go to the TensorFlow resources. There's tons of notebooks, tutorials, everything. At ALCF, use our Conda module for TensorFlow. So that one has one built by Kyle, who's probably here somewhere. It has the correct CUDA, the correct libraries for scaling out already included. And if you're running on the ALCF systems, there's some performance considerations for TensorFlow. So first of all, use mixed precision if you can. The A100 GPUs have the Tensor Core accelerator pieces, which will do even faster operations in TF32 or FP16. And the easiest way in TensorFlow to do that is with Keras mixed precision policy. And if you follow this link on the previous slide, you'll find out more about that. TensorFlow has this cool system called tracing, where you write a piece of Python code and you decorate it with this tf.function decorator. And TensorFlow will go through it once, see what operations you're using, and then take the whole thing and put it on a graph. And then it can do things like graph compilation, fusion, and other tricks to make it go faster. It does have a number of gotchas, so you can't do dynamic programming there. You can't have an if statement in a Python if in your TF function, unless you only care about the first time it goes through. So you have to be careful there. And if you want to use XLA, you have to use TF function. XLA stands for Accelerated Linear Algebra. It's an additional compilation tool that TensorFlow offers that will make your code go even faster in most cases, particularly with lower precision, so FP16. You can get a lot of fusions with XLA where it's taking some normalization and some convolution operations, one of which is memory bound and one of which is compute bound, and it puts them together, and combined they go much faster than separate. The flip side is that profiling XLA compiled code is much more challenging. Pytorch is another framework. So if you pull up Google Trends, Pytorch here in red is actually starting to become more popular than TensorFlow. One quirk I found is that on that site, TensorFlow is the only framework used apparently in Montana. There are 0 hits for Pytorch, but we're in Illinois, so Pytorch is popular. It's a lot more Pythonic than TensorFlow. It has recently added some graph compilation steps, but it's largely still early. We haven't tested it well ourselves. Your mileage may vary, but if you have any trouble with it or great success with it, please let the ALCF support team know, because we're interested to see how our users are doing with it. Out of the box, TensorFlow and Pytorch have comparable performance. It depends on your model. This one particular application, Cosmic Tagger, we did a comparison of Pytorch and TensorFlow XLA. And you can see that with XLA, TensorFlow is faster, but without that accelerated linear algebra compilation step, Pytorch actually beats TensorFlow for that model. And if you have models with many small operations, the compilation layer in Pytorch is definitely worth exploring. Pytorch makes reduced precision very easy. They have an automatic reduced precision tool. You can follow the link and find out more. They just updated to Pytorch 2.0, which is what we have installed in our latest Conda module, but it's backwards compatible with all the previous Pytorch releases, so it should be seamless. If you need to integrate Pytorch into a C++ code, or you need a particularly low latency application, Pytorch has a nice C++ front end. It's called libtorch. You can find it at this link. And they've also brought some high efficiency functional transformations similar to JAX that do things like Hessians, Jacobians, Jacobian vector products. If you need any of that thing and you already have a Pytorch model, that might be worth exploring. Personally, I haven't tried it. Pytorch, though, does have one of the biggest ecosystems of add-ons. So Gaussian processes, graph neural networks, geospatial enablements, and many, many, many more. So if you click this link to their ecosystem and you're thinking about, I wish I could do this in Pytorch, probably can. Someone's probably already done it and published a package. So if you need tools like that, Pytorch is really great. JAX is the last one I'll talk about, and the talk I gave this morning was entirely done in JAX. It's built on XLA, just like TensorFlow, but it actually gets right to XLA, and you don't have to go through this big, huge TensorFlow framework and tf.function transformations. You just write the Python code like it's NumPy, and XLA will compile it. It's purely functional, which is different from the other frameworks, so there's no side effects. You can't do in-place operations. But the thing it enables is automatic vectorization. So you can write a function that works on one image and then vectorize it automatically over a batch of images, or on any axis, actually. So JAX lets you do all sorts of things. It even lets you break your code if you like. There's a number of gotchas. They have a whole section of the JAX documentation that has the sharp bits and tells you all the things that you can do wrong. So click that link if you're going to try it. They also have the best auto differentiation documentation, I think, of all the frameworks, or even not frameworks. If you want to know what automatic differentiation is doing in your model, this link is one of the best ones from a mathematical perspective to follow. On ALCF systems, JAX is also installed in our Conda module. So officially, it supports scale out with this pmap function, which is parallel map. It's like vectorization, but instead of taking one image and turning it into 10 images, you take one image per GPU, for example. There's also an MPI-enabled MPI for JAX package, which works well as well. And they can be used in concert with each other. If you want to get complicated, you can do pmap on a node, MPI for multiple nodes, scale out. If you're bringing a project to LCF systems, for sure the easiest thing to do is to bring your existing code. The frameworks are typically already installed. We install the ones that are most common and that people ask for. If there's a framework that's necessary for your code and not installed, you can talk to us about how to get it. We've made sure that everything in our Conda modules works, with all the basic tests. But if it does break some weird way, let us know. But many things are built with the latest drivers, MPI, and you're most likely to have success using the Conda modules. That said, you can of course extend the modules. So virtual environments is the best way to do that. And there's some documentation on the support page for how do you actually make a virtual environment built on the Conda module and then install packages to it. You can do pip install with the user option if you're familiar with pip. But note that the ALCF systems typically share a home directory. So your home on Polaris and your home on Theta GPU are the same. And if you install something on Polaris, it might break what you're doing on Theta GPU. So it's typically not recommended, but we're not going to stop you, and you may find that it works for you. And if you want to install everything yourself, of course, TensorFlow and the whole kitchen sink, go for it. Conda is a good way to get your Python and a package manager. And if you have any issues or challenges, report to us and we can try to help. If you're bringing a new frameworks app or creating a new one on ALCF systems and you want to know what framework you should be using and what will work best on our systems or on Aurora, of course, you're welcome to come talk with us about your particular problems, but there's kind of some general guidance here. If you need CPU inference, TensorFlow or something that exports to Onyx is a good idea. If you want fast prototyping, Pytorch is generally considered the easiest. If you're doing differential equation solvers, you probably want JAX. If you need to scale out to all of Aurora, Pytorch and DDP and DeepSpeed are known to be the best scale out softwares, but until we get on Aurora, that may change. If you need to plug into C++, libtorch is a good fit, but there's also other techniques that I think we'll hear about later today. Or if there's anything else that's weird about your code that you want to do, and you want advice from the ALCF data science team, of course, come find us during a break or send an email or something. Okay, thank you. Questions?
Thank you, very nice talk. I have one quick question about distributed training framework. At some point, which version they introduced the elastic training test. I guess that's part of figuring out how to test that out.
By elastic training, do you mean, if one node goes down, your training keeps going?
Yeah.
Good question. That, of course, is a nice feature to have. I don't know that we officially support that type of workflow. Pytorch may. We haven't seen many users asking for it. Huiho is going to come up next and talk about distributed training, so you could ask him your same question, or maybe he'll just tell you up front if he knows. Okay.
Hi, great talk. So you talked about the C++ thing. If you want to couple, for example, a TensorFlow or Pytorch, libtorch is a good fit. Is there anything for Fortran as well? If I want to couple my machine learning model to Fortran?
It's against the rules, actually, to ask the Python team about Fortran, so I can't answer. To be honest, I have actually no idea. I've never compiled Fortran.
Okay, thank you.